Welcome back to Calc 2. In our class, we are just going to provide kind of a short introduction to differential equations. We're going to look at some of the stuff in 9.1 and more specifically 9.3. Many of you taking this course will have to take differential equations. You'll start at the beginning and you'll get everything we're going to do here in much more detail. And those of you who don't have to take it, this may be the only time you see differential equations. So let's start with exactly what is a differential equation. Well, of course, you've been working with them, right? We've been getting derivatives since Calc 1. Basically, a differential equation is an equation that contains your independent variable, some function, and that function's derivative. Essentially, the derivative is within the equation. When we talk about a solution to a differential equation, the solution to the differential equation is the actual function. So what we're going to do in this course is we're going to start with a pretty basic differential equation. We're going to learn how to get what we call the general solution. And hopefully some of this will remind you about when you first started working with the antiderivative in Calc 1. And we're going to integrate to get that general solution. And then we can look at a specific initial value to turn that general solution into a more specific solution. So that's pretty much the idea. We're going to do a little bit of classification first. We've kind of defined what a differential equation is. A couple ways you're going to classify them. You classify them by order. So the order of the differential equation is based solely on the level of the derivative within the function. So differential equations can be written a bunch of different ways. If we had the equation p prime equals kp, we have our unknown function p along with the derivative. Okay. In this particular problem, you would not know. You'd have to be given more information to understand that your independent variable in this case is time. Because another way, when you see things like p prime, it really doesn't give you enough information to know what that independent variable is. So often, another way you'll see it is written like this. All right, where p prime of t is now telling you that t is your independent variable. But the best way to actually work with it, the workable way to write your differential equation, same equation, is to write dp over dt. That's this p prime. We're going to write it as dp over dt equals k times p. Now you can clearly see what we are differentiating with respect to, and we're differentiating with respect to time in this particular problem. So these are all first order equations. There's a lot of different ways you can see a first order equation. Let's take a look at another example of a first order. Maybe we'll come back to this one later in the lesson. So again, that y prime, a bit problematic when we want to go to work with it. So we're going to change our y prime into t. T here is our independent variable. So we could rewrite that as dy dt cosecant t equals negative y cubed over 2. These, again, are all first order. What makes them first order is within the equation, you only see the first derivative, no matter which way it's written. A whole bunch of different ways it's written here. Second order differential equations get So your second order could look like, let's do x double n. This is clearly a second order differential equation because you have a second derivative in the problem. Another way to look at this is when you solve a differential equation, you integrate, you get a constant, which we're going to see in a moment. If you end up with two constants, that means your original was a second order differential equation. We are not going to look at second order differential equations in this class. They're certainly more complicated and best saved for when you actually get to differential equations. We are going to focus on these first order, and you can have higher order differential equations as well. Just a couple more little that really doesn't, not that it matters that much, but you also end up classifying them as homogeneous versus non-homogeneous. And this is another one you'll talk about much more when you actually get to the course. A homogeneous, simply no matter what the order it is equal to 0. So we have an x double t plus, say, x of t equals 0. That's a homogeneous, where if it was equal to something else, that would be non-homogeneous. So that's pretty straightforward. And of course, just like your regular equations, you can have linear and nonlinear. And as with your other equations, that is solely based on the function itself, and you're pretty familiar with what makes something linear versus what makes something not linear. But for this course, for our little introduction, we are going to focus solely on what do I need to do to get my differential equation back into a general form, and if I have an initial value, what can I do to use that initial value to get a very specific form of the equation. So let's start with let's do y prime cosecant t. So this is the one I think I had wrote earlier for an example of a first order. So we have a differential equation here. It's a first order. We have our independent variable of t. We have our y. We have our y prime. So the only thing we're going to do with this one is solve for what we call the general solution. Oops. So there's a couple things you have to do before you can go ahead and solve a differential equation. Number one, I would get rid of anything that's written as a prime and actually figure out what is my independent variable, what am I differentiating with respect to in this particular problem. In this particular problem, you can see it's a t, so it's dy dt. Okay. We have to perform, in order to solve it, we have to do what we call a separation of variables. Separation of variables. So this is pretty much essentially what is in section 9.3 if you read 9.3. So anything with my y's need to be together on one side of the equation, and anything with a t needs to be together on the other side of the equation. But we need to be careful when we do this. I really can't just divide by dy because my dy and my dt is going to be part of an integral that we have to integrate it to go back to solving it. I need to keep them not in a denominator, for lack of a better term. In other words, I can't just divide both sides by dy and say, well, my dy is everything with a y is on left-hand side and everything with a t, but that doesn't going to work because I have 1 over dt and 1 over dy, and that's not going to help us. We need dy in our numerator and dt in our numerator. So the best way to do that is actually to move your dt over to the other side. So then I have dy cosecant t. Now I need to move cosecant t over to the other side to match my dt. I'd have to divide by it, but instead of that, I think it's better if I change cosecant into 1 over sine t, because now I get to just multiply by sine t. And of course, you got to divide by this y cubed. So if I divide both sides by y cubed, so y cubed now has to come over here by dividing it out. This is all just basic rearranging an equation using algebra. The great thing is, and why we have to change our y prime into dy dt, is you can break those derivative fractions up because they become an integral part of your integrals that we're going to make very shortly. So what am I left with? I have dy over y cubed equals, I'll leave the negative over here, it doesn't matter, sine t over 2 dt. So this all, left-hand side all has t's, the right-hand side all has my y's. What I'm going to do is take the integral of both sides of that equation. I can leave the negative on the outside. And here's what's nice. This one is the integral of 1 over y cubed dy. And here we have negative integral 1/2 sine t dt. Very simple integrals that we can integrate. So go ahead and finish integrating those integrals. So when I integrate, was that y negative 3 becomes y negative 2. Yes, so that's negative 1 over 2y squared. Integral of sine t is actually negative cosine, so that negative goes away. So that becomes 1/2 cosine t. Now, technically when you integrate these, you would have a plus c at the end of both, right? Plus c, plus c. But we don't, one would be plus c1, one would be plus c2. Constants like this can get absorbed into each other because they have no variable in them. And we can absorb them in such a way we only need to put one big plus c there. So to write our general solution, all you really would do for the general solution, you just solve for your function. In this case, it's y. It's not always going to be a y. It could be something else. But in our problem right here, it's a y we're going to solve for. So this is a little tricky. One thing I can do is multiply both sides by 2. Or multiply both sides by 1/2. Let's get rid of that and let's move that negative back over. Remember, it's a constant, so you don't need to move the negative to the constant. If I multiply both sides by y squared and divide by negative cosine t plus c, I end up with y squared equals 1 over right? Because you need to think of this as a grouping. And then I have y equals plus minus square root, because we're taking the square root of 1 over, and I'll write this as c minus cosine t. So that would be our general solution after we solved for y. So if you're just asked to find a general solution, it's going to have a c in it somewhere. Just solve for your y. That most of them have y's, but some have other. You basically, you're solving for whatever variable is here. All right, that's what you're solving for. Okay, now let's move on to what we call our initial value problems. You'll see these a little bit in 9.1 and also in 9.3. This is where we want to get a more specific solution. So again, think back when you first learned about antiderivatives, you had plus c on the end, and you learned that your function that you're going to integrate, your answer, your integration is actually the function. You end up with essentially a family of functions, we call it, right? So you have a slope line, that's your derivative. You want to go back to the original function, you actually get multiple functions because of this plus c. And the only way we were able to get a specific function is to get basically one of the value points. If we can get 1 point, then in this case we call it our initial value. So let's look at a basic problem. So we'll do y prime of t, so we know what we're differentiating with respect to, y to the et. But we also know, or will be given, our initial condition. So this is our initial condition. All right. Y of 0 equals -1. So we're going to come back to that initial condition after we solve for it. Do like we did in the last problem. Separate our variables if we have to. And get our general solution. We'll come back to this initial condition. But what this initial condition actually gives us is our y value of -1 when our independent, which is t in this case, t equals 0. So that's what that's going to give us. All right. So again, to start, this y prime of t, you want to write as dy over dt. So we can work with it. So pretty easy. The dt has to come over to the left-hand side. The y comes over to the right-hand side. So doing that, we end up with 1 over y dy, e to the t dt. Go ahead and integrate both sides. It's going to give me ln y equal to et plus c. Right, don't forget your absolute value. We can solve for y. The only way you can do this, though, is to actually, right, all of this gets raised up to e, and that has to get raised up to e. So ELN cancels away, and you're left with y, and this is crazy over here because it becomes e to the et plus c. But now, I want you to recognize something from basic exponents. Isn't x to the 5th equal to x cubed? Right? Right? Do you remember this? When you multiply bases together, you add their exponents. So in other words, by following that rule, right, I can kind of rewrite that as that one. Now, Because e to the c is a constant, again, you can, if you choose, you can actually, you can choose, I'm not going to because it really doesn't make difference to let e to the c, since there's no variables in that, c is a constant, e is a value, it's a constant. You can let that just be a new constant a if you don't like working with e to the c. It's really not going to make a difference. So I'm going to leave it in there, but you can change it if you want to. This is our general solution. Right? This is what we would call either of these. The one above or this one is general solution. Okay, remember what that initial value was? Y sub 0 equals negative 1. So that means y equals negative 1 e to the 0. Okay. E to the 0 is 1. So negative 1 equals e to the first times e to the c. I need to come up with this. All right. Or if you made it an a, you would have a, e to the t, and you're going to come up with that. So I got to solve for this. So what does that look like? E to the c, my constant value, is negative 1 over e. So you're just going to rewrite this function. E to the c part is negative 1 over e times e times e to the et. Right? So that's what I have. So there's my e to the et. My red e to the c, right? You follow it? Became that. And there really isn't much you can do with that. That is your solution. That's all it looks like. Y equals, and I guess you could have negative e with a negative on the outside. Combine it. You don't have to. You could combine it into negative e to the et minus 1 because just following the rules of exponents because you got e as your base. All right, that's your, so we had our general solution, and your initial value gives you a new solution that has no c in it. All right, so let's just take a look at another one. Yeah. So I have dy dt, do you see we're going with dt here, equals ln t, I'm going to write it this way, over t e to the y. All right, so you got to separate your variables. Yeah, so ey has to come over to this side. So that actually becomes ey dy. And this side becomes ln t cubed dt. I don't know where I was going with that extra t. Go ahead, integrate. Occasionally, as you're going through some of your math labs, you will come across a problem where you absolutely cannot separate your variables. All right. You're going to try it and there's just no algebraic way it can happen. In which case, if you're doing a math lab problem, you're always going to get this option of cannot separate variables, in which case you're done and you move on. Okay, just wanted to point that out. We're working on ones that you can separate, but you do come across things that you cannot separate. And that's another thing you'll discuss further when you get to your differential equations class. Okay, so your quick integration, this is e to the y. Just use your u, let u equal ln(t), right? Just do your u sub. And if you do that, you end up with u to the third, which becomes u to the fourth divided by 4. So it becomes 1/4. U is actually ln(t) to the fourth plus c. Again, here we go. General solution, sort of. It's not quite the general solution because you would need to solve for y, which means you then have to ln both sides, and it gets a little complicated. If you're asked for a general solution, you will need to go through that process where you take the ln of both sides, but we're actually looking for the initial value to that specific when y sub t equals 0. Y sub 1 equals 0 when t is 1. So it might be best just to leave it like this until we finish it, because we need to solve for c. To finish it, well, we just said y is 0 when t is 1. Right, so 1, you can see how quick this comes out. ln 1 is just 0, so that's just, yeah, c equals 1. So now I can plug it into my general. Now that I've plugged it into the general, I can now solve for y. We didn't need to solve for y yet. We no longer have a problem with c in it. You solve for y by just ln'ing everything, okay? Because that gives me y equals the natural log . And that's because this ln(t) on the inside is being raised to the fourth power. You cannot just pull the 1/4 over. You got to be careful there. So that's it. All right, that is it. Let's do one more, and then sure. Here we go. One more example. Y prime equals 2x. And the initial value, y sub 1 equals -1. All right, notice we don't have t's in this one. Our independent variable is going to be our x. So we have y times dy dx. So get your dx over to the left-hand side, get that denominator over to the right-hand side, and that's going to give me y 2 plus y squared squared. Integrate. And you can integrate these y's. You would have to do a u sub. I would let u equal 2 plus y squared. Du is then 2y. And you're going to need a 1/2, so it's going to give us what? 1/2 integral of u squared du, which is 1/2 u cubed over 3. When I put my y back in, I'm doing the u sub really quick, is 2 plus y squared cubed over 6 I end up with. And this one's just going to be x squared, right? 2x squared divided by 2 plus your c. So again, let's get our c before we try to simplify this in any way. So y sub 1 equals -1. Remember, when y sub 1 equals -1, y is the -1. And our independent variable, which in this case is our x, is 1. So what is that going to give me? 2. Well, -1 squared is 1. Plus 1 cubed over 6. 3 cubed is going to give me 27 over 6 equals 1 plus c. So -1 equals c, minus 6 over 6. So that c is 21 over 6, which is, you divide by 3. 7/2. So cleaning it up, let's see what we have. Where's our problem? There it is. So we have 2 plus y squared cubed over 6 equals x squared. Right? So what is that? That's 2 plus y squared cubed equals back our 21, right? Because 3 times 7 is 21. This is going to get a little messy if we try to solve for y, because it becomes 2 plus y squared. I got to take the cubed root, right? You may be okay, even in math lab, just entering it in that form, right? Because you have to take the cube root of both sides. Yeah, it's just going to be a little messy, right? -2, and then you got to take the square root. So it actually looks like this, which is nuts. All right. Yeah, somehow this just looks better than that. But if MATLAB makes you, solve for y itself, that's going to say what it is going to end up looking like. I think that should give you a nice little sampling of how to go from separating your variable, separation of your variable, solving your differential equation to a general solution using an initial value then to get to a specific solution. So that is all we're going to do with differential equations in this class. Those of you moving on, you will get an entire semester of it.